Okay, welcome to chapter 20 on carbohydrates. In this is a lecture video, not to be confused with one of the review videos that has already been posted. And in this video, I will be going over the first few sections here up to the oxidation and reduction of monosaccharides. In a future video, we'll finish up the chapter with disaccharides and polysaccharides. Okay, before we begin talking about carbohydrates specifically, I want to cover the carbon cycle. So plants are amazing organisms. They are able to take carbon dioxide gas from the atmosphere, water, energy from the sun, and through photosynthesis are able to create carbohydrates. In the process, they also produce oxygen. So oxygen here. So a couple key things about this. So they take energy, water, and carbon dioxide, and they make carbohydrates. Through cellular respiration, animals, such as us, or horses in this case, will take carbohydrates in along with oxygen in the atmosphere. So one of the products of photosynthesis is oxygen. We're going to take that product along with carbohydrates and get energy from it. Okay. So in some ways, respiration is the exact opposite of photosynthesis. Whereas photosynthesis takes in carbon dioxide and water, and so the respiration we emit. Right? So the horse is going to exhale carbon dioxide and water. In the process, we'll produce energy from this. This energy ultimately came from the sun. Right? The sun was used to produce the energy for photosynthesis. That energy is returned to us when we break down the carbohydrates in metabolism. So metabolism has two main parts. Metabolism. There's catabolism. In catabolism, we're going to go from complex molecules to simpler molecules. To simple. And in the process, we produce energy, so surplus of energy. The other half of metabolism is anabolism. Here we're going to go from simple, the simple compounds might be something like a monosaccharide that we'll talk about later, and then it is incorporated into a polysaccharide, or in a later chapter we'll talk about individual amino acids that get incorporated into proteins. So anyway, from simple to complex, and whereas catabolism produces energy, here this uses energy. So energy is required. The energy that's used here is energy here that was produced in catabolism is then used in anabolic reactions. So there are three main types of monosaccharides, and it's just coincidence. However, it turns out there's many different types of monosaccharides, but we're going to talk about three main types. Let me use black. So we're going to use talk about three main types of monosaccharides. We have glucose, fructose, and galactose. And as I said, in a later video we'll talk about disaccharides and polysaccharides. Well, it turns out there's many different types of disaccharides, but we're also going to talk about three main types of disaccharides, and it's kind of 3, maybe 4 types of polysaccharides. So in this lecture, we're going to focus on the monosaccharide. So what is a monosaccharide? It is a polyalcohol, so carbohydrate, polyalcohol that contains either an aldehyde or a ketone. So it's an aldehyde or ketone. The chemical formula here, there's 1, 2, 3, 4, 5, 6 carbons. So down here, I will write C6. And if you would look at this structure, for every single carbon, there's 1 oxygen. So C6, we'll figure out the hydrogens in a moment. And there's also 6 oxygens. If you were to count up the hydrogens, turn out to be 12. So if we look at this, we've got a bunch of carbons, and then we have twice as many hydrogens as oxygens. So one way you could write this structure, or this formula, would be C6, and I'm going to put a dot here, dot 6 H2O. Now, in your general chemistry or basic chemistry class, you might have been familiar with something like copper sulfate. Copper sulfate exists as a hydrate, so dot 6. It also happens to have 6 waters as well. These waters are not ionically bound to the copper sulfate. Instead, these waters are more or less trapped in the crystal structure. So if we were to maybe draw a crystalline lattice here, right, so there we have a crystal, and you have maybe a copper at one corner and a sulfur or a sulfate at another, and they form this crystalline lattice. Well, inside that crystalline lattice, for each copper sulfate, you have 6 waters. So I just put in 6 H2O. They're not covalently or ionically bound, they're just simply trapped. And because of that, we can heat this up. If you remember doing this lab in basic chem or general chemistry, you can heat this up. Put a little triangle here, we heat this up, and you can drive off the water. So now we have just plain old copper sulfate. This would be anhydrous, and 6 waters of hydration come out as gas or steam as you heat this up, just as if you were drying clothes, right? This is essentially the water, the moisture that's trapped in your clothing gets driven off when you heat it up. Same thing happens here. Well, if we look at the chemical structure here, it looks like we have these waters of hydration combined with carbon. So this is carbon, it's a carbo, and these waters are waters of hydration, so carbohydrate. There are also some chemical reactions which make carbohydrates appear to be hydrates of carbon. However, you can do this reaction. If you were to take, you can do this reaction at home, a little chemistry lab at home. Take some sugar, some sucrose, some table sugar, it's the carbohydrate. Put it in a tablespoon, heat it up over the flame of your stove, and do it with a spoon that you don't care about too much because you kind of ruin it a bit. And you will get carbon, and the waters are driven off. But this carbon is that like charcoal, black charred stuff that can't, and it kind of sticks to the spoon, and you have to scrub it off. Unfortunately, you cannot run this reaction backwards, so you can't just add water to this and go back to the carbohydrate. You've broken the bonds here by heating it up. You've broken these covalent bonds. But if it was a true hydrate, like copper sulfate, you could just add water back and you would get back to the hydrate. So although this is another instance of what we call a misnomer or misnamed, carbohydrates are not hydrates of carbon, but if you look at the chemical formula, it kind of suggests that this is what's going on. What they really are, they're polyalcohols with an aldehyde or ketone. So in every single carbon is an alcohol, except for one where we have either an aldehyde or a ketone. So monosaccharides have just one aldehyde or ketone unit. These are glucose and fructose. There's also galactose we'll look at. A disaccharide has two of these monosaccharides joined together. So one of the disaccharides we'll talk about later is lactose. Okay. So a disaccharide here has two aldehyde or ketone subunits. Subunits, and it is difficult to see how they are come together here, but we'll talk more about these disaccharides in a subsequent video. But we have this is lactose, one of the disaccharides, and it is composed of two different monosaccharides, galactose and glucose. So they form these ring structures that we'll talk more about later. We also have polysaccharides. Right? So polysaccharides means many. So we have many aldehyde or ketone subunits. Again, each circle here, each ring structure here is one monosaccharide monomer. If we put many of them together, we can form a polysaccharide such as starch. Well, the vocabulary, this text here got messed up. There's something called an aldose. Put it here. By the way, you might have guessed as much. So alcohols end in OL, amines end in INE, carbohydrates end in OS. We have fructose, galactose, lactose, they end in OS. So an aldose is a carbohydrate with an aldehyde. So how do you say carbohydrate with an aldehyde functional group. A ketose, as you suggest, has, as you may have guessed, has a ketone. So the one ketone or ketose that we will focus on is fructose. There's also this term pentose and hexose. Pentose, like pentane, has 5 carbons. Hexose has 6 carbons. So this glyceraldehyde is what we call a triose because it has 3 carbons, as is dihydroxyacetone. Now, this is an aldose, so it's an aldotriose. Aldotriose, because dihydroxyacetone is a ketose, we would call this a ketotriose. Glucose is an aldose, it has an aldehyde, and there's 6 carbons, so it is an aldo for aldehyde, and there's 6 carbons, so hexose. Aldohexose. So there's hexoses, pentoses, trioses, tetroses would be 4, but we're not going to see any of those. Hopefully before you've watched this video, you watched the videos on stereochemistry. You notice that each of these carbons here, there's 6 carbons altogether, but 4 of them, this carbon, this carbon, this carbon, this carbon, and this one, those are all chiral. So if you don't know what chiral means, you better go back and watch those lecture videos on stereochemistry. So, brief review. Chirality, or chiral, means there's 4 different atoms or groups of atoms attached. These carbons are chiral. So instead of drawing every single carbon like this, we use this what's called a Fischer projection. So there's a famous chemist named Emil Fischer who came up with this. And I won't go into all the conventions, but essentially all you're going to do is take this carbon that was chiral, and you're not going to list it. You're just going to make kind of an X marks the spot. So this is that chiral carbon. The conventions as far as whether bonds are going towards you or away from you are very important, and if you were in my organic class, I would ask that you know that. But for now, all you need to do is identify the chiral carbons and recognize one enantiomer from another. So if you notice, remember now, enantiomers are mirror image isomers. So if we were to take this molecule and place it up in front of a mirror, this would be its reflection. This alcohol group, this hydroxy group, is on the right. In the mirror, it would be on the left. The hydrogen is furthest away from the mirror in the object, in its mirror image. Okay, it's on the right, and it's again deepest into the mirror. Top and bottom don't change, but in a mirror, but left and right do. What they're pointing out here, this is rather important. Naturally occurring carbohydrates are all D. So this is the D enantiomer. Its mirror image would be the L enantiomer. D and L are mirror images, so they're mirror image isomers. By the way, D carbohydrates, I said D carbohydrates are naturally occurring. L carbohydrates, not only are they unnatural, what we mean by that, they don't exist in nature, you have to make them in the laboratory. They are not metabolized by us. We cannot use L carbohydrates, only D. Okay, so here they've taken glucose, again it's an aldohexose, and converted it to a Fischer projection, so it's a little bit easier to pick out the chiral carbons. There's 4 of them. And we have right, the alcohol groups, now just focus on the alcohol group, is right, left, right, right. I could draw the mirror image of this, so let's say this is a mirror this is the mirror. The top and bottom don't change. But the left and right do. So this OH here is closest to the mirror. It will be closest to you. Whoops. How do we erase that? Here, this alcohol group is on the left. In the mirror, it'll be on the right. These two are on the right. In the mirror, it'll be on the left. Hydrogens, and so now I've drawn the enantiomer. This is L glucose, not naturally occurring. Other names for glucose that you should know are deep glucose, dextrose, blood sugar. The reason it's called dextrose is because it is dextrorotatory, which means it rotates plane polarized light to the right in a polarimeter. And again, if you don't know these terms, look at that video on stereochemistry. Blood sugar, or grape sugar, would be another word for it. So when people test their blood sugar, what they're looking for is this compound glucose in the blood. Does the D in D glucose mean dextrorotatory? No. It's again, this is another one of those misnomers. D glucose happens to be dextrorotatory. Is dextrorotatory. So rotatory. So if we were to put this in a polarimeter, it would rotate light to the right. L-glucose then would be, because it's a mirror image, it would rotate it the other way. It's what we would call level rotatory. It would rotate light in the opposite direction, counterclockwise. Here, this is a clockwise rotation. But the D and the L actually don't mean that anymore. Maybe at one time chemists thought that that had something to do with the optical rotation. It doesn't. What it means now is the carbon, you're only going to see conventional Fischer projections. They don't have all the carbons in here, but there would be 4 in glucose, 4, 1, 2, 3, 4, and it actually would be right, left, right. All it means is this carbon here that's furthest from the aldehyde or ketone, so the one closest to the bottom, not this one. This carbon is not chiral. This carbon is chiral. If the alcohol group is on the right, it's D. Of course, it's mirror image. This alcohol group is on the left, it's L. And that's all the D and L stand for anymore. So again, here we see D and L glucose. I already drew these before. The alcohol group's right, left, right, right. It's mirror image, left, right, left, left. One thing I should say about enantiomers, term enantiomer. Okay, so what do we mean by well, the only difference between these two compounds, between a pair of enantiomers, so one thing to keep in mind is enantiomers exist in pairs because they're opposite. It just says left and right are a pair and they're opposite. Up and down is a pair. Good and bad, a pair, they're opposites. So they exist in pairs, they're opposites. But the only physical property that differs between them is this optical rotation. So they have, because they're isomers, they have the same chemical formula. Right? But different properties. But the only physical property that's different between them is optical rotation. They have different optical rotations, as I mentioned before, rotations. One would be dextrorotatory, one would be level rotatory. So if it rotates light to the right, another word for that, we'd call that the plus enantiomer. If it rotates light to the left, we call that the minus enantiomer. Again, they exist in pairs. For glucose, it happens to be D and L. Actually, I'm not going to even write that down because I don't want to confuse you. But they would have the same boiling point, melting point, density, solubility, all the other physical properties. I spelled solubility wrong. They have the same physical properties except for this optical rotation. One key thing that they also have different is different chemical properties. So what's the difference? Oh, so that's why I started talking about this. Okay, so this question here, what's the difference between a sugar and a carbohydrate? Sugars taste sweet. So all sugars are carbohydrates, but not all carbohydrates are sugars. Sugars taste sweet. And so generally these are mono or disaccharides. Carbohydrates, as we mentioned, they just happen to have these polyalcohols with aldehydes or ketones. A carbohydrate that doesn't taste sweet is simply just a carbohydrate. So polysaccharides. Polysaccharides are not sugars. Sometimes they're referred to as complex carbohydrates, polysaccharides, but not complex sugars. These are complex, I just write down complex carbs. Okay, but they're not sugars because they don't taste sweet. So when I talked about the different chemical properties, if we're talking about glucose here, glucose would taste sweet, and we can metabolize it and get energy from it. L-glucose, it's very expensive. You can only get it from a chemical supply company that synthesizes it in the laboratory. It does not exist in nature. I don't know what it tastes like, but I doubt that it would taste sweet. So I'll just say does not taste sweet, and it's not metabolized. Because if you think about this chirality business means handedness, right? So your hands are chiral. Chirality. Handed. That's right. We have a right and left hands. If you think about gloves, and we're not talking about exam gloves, rubber gloves or something, we're talking about normal, like a pair of winter gloves. Your right hand, say this is on the right, so let's say this is a D-glucose, that will fit in a right-handed glove. It will not fit in a left-handed glove. And what I mean by that is, the way we taste things is these molecules bind to receptors in our taste buds, on our tongue, and they're designed to fit one enantiomer but not the other. So if this is your hand, it fits into the glove, that receptor on your taste bud. This one would not. It's like trying to put your left hand into a right-handed glove. It's just not going to work. It will not fit. Alright, so I mentioned the 3 common carbohydrates, glucose, galactose, fructose. You do not have to know the structures of these. I don't care if you know it's right, left, right, but what you should know is that this last guy is on the right because it's D. This alcohol group, the last one in the carbocarbon, furthest from the top, right? Also on the right it's D. Even fructose, this guy is D, so you should know that. You should know that glucose is an aldohexose, 6 carbons, so C6, and it's an aldehyde. Galactose is also an aldohexose. So again, 6 carbons. Fructose, 1, 2, 3, 4, 5, 6, a hexose. But look here, it's a ketone, so it's a ketohexose. Another thing you should recognize here is that glucose and galactose, these are not enantiomers. Enantiomers. Instead, we refer to these guys as diastereomers. What is a diastereomer? A diastereomer, okay, first off, they're isomers, so they have the same chemical formula. Okay, but if you notice here, let's just look at the alcohol groups. It's right, left, right, right. In galactose, it's right, left, left. So this carbon is different. Left, and again right because it's D. Okay. So they differ at least 1 chiral carbon. Okay. For diastereomers, they must differ at least 1 chiral carbon. So that means for diastereomers that the prefix here di means you have to have at least 2 chiral carbons. I should say have 2 or more chiral carbons. And the orientation about those chiral carbons, orientations, whether this alcohol group is on the right or on the left here, the orientations differ at least one chiral carbon, but not all. Not all. Okay? What would happen if here they just differ at one? Well, there's 4 different chiral carbons. They could differ at this one, they could differ at this one, they could differ at this one, but if they differed at all 4, they wouldn't be diastereomers anymore. Right? We're talking about diastereomers now. If they differed at all, that is to say, if they had opposite orientation at all, then they would be enantiomers. So again, I can draw the enantiomer of D-glucose. Here the alcohol group's in the right, so it's going to be left, right, left, left. So they differ at every single chiral carbon. This would be L-glucose, the enantiomer. So D-glucose, D-galactose, these guys are enantiomers. They're both aldohexoses. They are not enantiomers of they're not diastereomers of D-fructose because D-fructose is a ketohexose. Okay, so here we see the aldose family. All these guys down here, these are the aldohexoses, and these guys are all diastereomers of each other. Diastereomers. Okay. And these are all D, so this is the D family, or I should say the D enantiomers. The L enantiomer, so just look at allose, they're all on the right. L-allose would have the alcohol groups all on the left. So the 3 that you need to, actually there's just 2 here, but well, there's maybe 3. There's glucose and galactose. Don't have to know the structures of these, but you should know that this last one, alcohol group, is on the right because these are D and they're naturally occurring. Glucose and galactose and diastereomers. Don't have to know any of these others. One other that you should know, however, is ribose. And the reason for that is ribose, okay, it's an aldopentose. So, aldopentose. And maybe you're familiar with DNA or RNA. Right? Ribose is the ribose in ribonucleic acid or deoxyribonucleic acid. So that's where ribose comes in. Okay, so in chapter 16 we talked about acetals and hemiacetals. This had to do with these are addition reactions. We add an alcohol to an aldehyde. This bond kind of opens up and we get the OH. So this oxygen here is this oxygen here, and then this OH, right, becomes the ether. So this R group is R prime here. So remember, a hemiacetal is you have an ether, carbon, oxygen, carbon, and an alcohol on the same carbon. This carbon here is referred to as a hemiacetal carbon. Okay, so here we have 5-hydroxypentanal. It's a polyfunctional molecule. We have an aldehyde and an alcohol, and you can just draw it straight like this, but you can there's flexibility in this alkyl chain and these carbon-carbon single bonds, and so you can kind of wrap these guys around, and what you end up getting is one part of the molecule interacting with the other part of the molecule. So this forms a bond here. There's a carbon here. This oxygen forms a bond with this carbon. Right? That's this carbon-oxygen bond, right? This aldehyde carbon, right? This carbon number one, well, we number from the most highly oxidized group, so the aldehyde starts at number 1 here. This is now the hemiacetal carbon. And it forms a cyclic hemiacetal. Right? So this carbon here is now a cyclic hemiacetal. The reason we talked about hemiacetals back in the chapter on aldehydes and ketones is because this is what you see with carbohydrates. So yes, this is a hemiacetal. Right? Carbon, oxygen, carbon, there's the ether linkage. Here's the alcohol on the same carbon. This hemiacetal carbon is now what we refer to as the anomeric carbon. So the hemiacetal carbon is also the anomeric carbon. And the neat thing about this is when this bond forms, right, this carbon here, carbon number 1, that's going to become the alcohol. Right? The alcohol group can either be down or it can be up. If it's down, we call it the alpha. So that's the Greek letter alpha. So this is the alpha anomer. If it's up, it's beta. And this carbon was not here. In the open chain form, let me just go back to, right, in the open chain form, this carbonyl, the aldehyde, is not chiral. It's not chiral. Once you form the hemiacetal, guess what? It becomes a chiral carbon. So we form a new chiral carbon. A new chiral carbon is formed, and what we have here are the new type of isomer we refer to as anomers. If it's down, it's the alpha anomer. If it's up, it's a beta anomer. These are not necessarily mirror images of one another. It's a new type of isomer, right? So a new type of isomer called an anomer. This becomes really important too. So, why should we care if it's up or down? Stay tuned, that'll be important in a moment. So, focus on this structure in the center. This is glucose, D-glucose, and I won't get into the conventions here, but remember, this would be carbon number 1. Carbon number 2, the alcohol group was on the right. So it went right, left, right, right. In fact, let me just go ahead and draw. So you can see that there is some rhyme or reason to this. So the aldehyde group on the top. The 4 chiral carbons, 1, 2, 3, 4, and then CH2OH. It was right, left, right, right. Again, this is D-glucose. Glucose can be abbreviated GLC. So if it's on the right, here you see it's down. On the left, that's the other side, now it's up. So just as there's a right and left, there's an up and down when you have a ring. Remember we had cis and trans cycloalkanes, and so here these guys are in opposite. So it's right, left, right. Now this becomes part of the ring, so it's not down. This oxygen becomes part of the ring. So we went from 1, 2, 3, 4 chiral carbons, right? Now we have, again, we're not going to remember this. There's carbon number 1. There's carbon number 1. In just counting the number of chiral carbons, there's 1, 2, 3, 4. Here we have 1, 2, 3, 4, but this is chiral as well now. And so this can cyclize, right? This oxygen can bond to this carbon, and when it does, it can either be up, it's beta, or when it's down, it's alpha, these two different anomers. Notice they're in equilibrium, so they're always flipping back and forth. In solution, just a little bit of it's actually in the open chain form. It's more stable in this cyclic form. 37% in the anomer conformation, or isomer, and 63%, so the beta is favored. And the reason for that is if you look at this here, the oxygen here, right, it's not near anything else, right? It's not near this oxygen here, but when it's down here, this oxygen and this oxygen are kind of close together, and there's something we call steric strain, and so that disfavors this form, so it prefers to be in the beta conformation if it was just the monomer. So this cyclic form here, the cyclic hemiacetals that we form with these guys, these are known as Haworth projections. So we don't have a Fisher projection. Let me just go ahead and draw the Fisher projection again. That's where we don't show these carbons. I won't draw the whole molecule, but it's right, left, right. If it was D-glucose. This is known as, again, the Fisher projection. Haworth is when it forms this ring structure. So there's conventions to this as well, whether the carbons are up and down, and I'm not going to get into that level of detail. What I want you to be able to pick out is carbons 1 through 6. So 1, 2, 3, 4, 5, 6. Carbon 1 here, this is the anomeric carbon, or the hemiacetal carbon. So the anomeric or hemiacetal carbon is this carbon number 1 here. So we had two aldoses, glucose and galactose, but we also had our ketose, that was fructose. So notice fructose here, if you recall, for the aldoses, the alcohol group on carbon 5 reacting with the aldehyde on carbon 1, but now the carbonyl is in carbon number 2, so it's going to be carbon 5 and carbon 2. So here we go. Carbon 1 just has, it's not chiral, just has, because it has 2 hydrogens. Right? So carbon number 2 is the anomeric carbon. 3, 4, 5. The alcohol on carbon 5 reacts with the carbon on carbon 2, and that means we get a 5-membered ring instead of a 6-membered ring. Okay, these are well, I won't get into the details here. They're called a furanose, but the main thing here is it forms a 5-membered ring, not a 6-membered ring. Remember the aldoses, we had something that looked like this. And this anomeric carbon, if it's down, it's alpha, right? And then the oxygens are down, up, down, and then carbon 6 up here, CH2OH. Okay, so it formed a 6-membered ring. That's where the aldose is, because the aldehyde was on carbon 1. Here the carbonyl is on carbon 2, so it forms a 5-membered ring. And by the way, fructose is the only ketose we're going to be looking at. So it's very easy to pick out when it's fructose because it has this 5-membered ring versus a 6-membered ring of glucose and galactose. I won't get into the details here, but you should recognize this is the same sort of thing we've been talking about for a while, oxidation. If you oxidize a aldehyde, you get, well, here they're doing the reduction. You're reducing the aldehyde to the alcohol, right? So this is a reduction. Glucose becomes glucitol. This is, or sorbitol is the name. So this OL, right, is an alcohol. So we go from the aldehyde to the alcohol when it's reduced. Xylose. By the way, xylose, I won't get into the details of xylose, but it's, I had a neat show and tell for xylose if we were in regular class, but it's, I can't even show you now because it was left in my office, and I can't get into my office now because of COVID. So anyway, xylose is this compound. If we reduce this aldehyde to the alcohol, we get xylitol. Xylitol is found in a lot of sugarless gums and whatnot, and the only thing I want to point out here is that it can be very toxic to dogs, right? So, highly toxic. I think it causes liver or kidney damage, I'm not sure. But, so, keep your sugar-free gum and whatnot away from your animals so they don't chew on this stuff and get sick. So oxidation, I think you did this one in lab, or at least it was slated for lab. I don't know because of COVID, I don't know what lab you did, but if you oxidize the aldehyde, you get the acid. Okay? So glucose becomes gluconic acid. And this is where we talked about reducing sugars and non-reducing sugars. So what do we mean by reducing? Copper 2 is blue. This is the either the Benedict's or the Fehling's test. It just depends on what the pH, what conditions it's done. It's either the Benedict's or the Fehling's tests. You take copper 2, which is blue, right? So this is a blue solution, and if you react it with a reducing sugar, the copper 2 becomes copper 1. This is now, I won't get into the details here, but now this is copper plus 1. So it went from copper plus 2 to copper plus 1. The copper was reduced. And if you have a sugar that can reduce copper from copper 2 to copper 1, it's referred to as a reducing sugar. So reducing sugars have an aldehyde because you can reduce the aldehyde, right, to the you can oxidize the aldehyde to the acid. So they have an aldehyde that gets oxidized to the acid. Non-reducing sugars do not have an aldehyde. They do not have an aldehyde. They do not produce Fehling's reagent, so you get a negative Fehling's or Benedict's test. So I just got done saying that reducing sugars have an aldehyde, but even some ketones, it says ketones here, but it should be some ketones, easily oxidized. They're special ketones. What that means is the ketone has to be on the next to last carbon, or what they call the penultimate carbon. If it's interior, one of these other carbons, it will not work, but if it's on the next to last carbon, it can rearrange and it will give you the aldose. Okay? So fructose can rearrange. Remember, fructose is a ketose, a ketone. It can rearrange to give you this compound aldose. These guys, again, they're just they're not optical isomers. They're not diastereomers or anomers or diastereomers. They're just different structural isomers. So aldose now. Right? This actually is an aldose. So the ketose becomes an aldose, and these guys are structural isomers. They're not optical isomers. And because of this rearrangement, forming the aldehyde here, now it is reducing. So this guy is reducing. And even though this is a ketone, generally ketones are not reducing. But if it can rearrange to give you an aldehyde, and this is in equilibrium, then once it forms this guy, we can react it with the copper in Phelan's or Benedict's test and get the acid. And so the aldehyde becomes the acid, and the blue, right, this is blue, becomes red. And they say brick red. It's really kind of a muddy color. But too bad you didn't. I don't know if you got to see that in the video or not, but that's what happens. Disaccharides. So we will talk about disaccharides in the next video.